Moving on to the next one. Again, cool. So moving on to the next one. Again, an extension of the previous setup, but just that there are two circles here. So there are two circles of radius 10 and 10 root 2. So we'll make the other one slightly bigger. Intersect at two distinct points. Okay, so basically they are intersecting like this. Tangents are drawn from respective centers to the meeting points A and B such that AB is a common chord. So basically these were the meeting points A and B. Tangents are drawn from the respective centers. So the center is here and here, and similarly here and here. At the to the meeting points A and B such that AB is a common chord, which it will be. And these are tangents, right? So again, just to sort of put it into perspective, that both of these essentially would be equal because again tangent from the same point, right? So length of the common chord, again, this is the center of this one, this is the center of this one. So here this would then be perpendicular. You sort of have this bisection of the chord, and you can figure it out. And this again is a similar, like is one of the standard setups that you will see for the length of the common chord. So you know the radius. The radius is 10, and you will follow. So this is 10 and this is 10 root 2, right? So here in this case it is like, for example, like here if you see, okay, let's just give a couple of minutes for you to try, right? Like if you had to find the length of the common chord, we just covered a very similar question behind. So how would you go about finding it? So please try this once and then we'll see how it is to be done. Only focus on part A for now, part B we'll see.
Hello.
Hello.
Yeah, we can use Pythagoras theorem.
Sure. Tell me and I'll keep writing down. How have you done it?
So the angle made by the first center and A and second center and B will be 90 degree.
Yeah.
And
Perfect.
so the length PQ will be 10 root 3. And the chord will be bisecting that PQ. So it will, half of that will be 5 root 3.
Yeah.
And so 10 square minus 5 root 3 square will be half length. So we can double that.
Absolutely. Yeah, that's the correct approach. The only catch was, again, because this should be 90 degree, and then you can use directly Pythagoras here. And yeah, and then you can find this and you will have it. The other way to do it would have also been like in the last stage, instead of the Pythagoras itself, Pythagoras is absolutely fine to use in like this triangle, but also you could have just equated the areas and gotten the height, right? Like half into 10 into 10 root 2 would be equal to half into base. Base you did calculate correctly by Pythagoras as like 10 root 3 or whatever, and then the height. So this would have given you the height, and 2h is your answer, right? So cool. So that's correct. Now the second part of, so it was a pretty direct one, right? But again, since this is a common plane, yeah, sure, please go ahead.
Sir, but if we took them both the parts as 5 root 2 each, then Pythagoras theorem won't satisfy for the triangle AQO.
Can you repeat the question, please?
Sir, if the midpoint where they are joining, if we say that is O, and then we say that PO is equal to OQ, which is 5 root 2, but then then it won't be, the Pythagoras theorem won't satisfy for AOQ.
Yeah, so that is why what you will have to do is, like basically if this is the height and this portion is x, this portion is y, that is what you're saying, that right, that this x and y may not be equal.
Yes.
Yeah. So but the height will be equal. So what the way you can use Pythagoras is basically to say that x square or 10 square minus x square will be equal to 10 root 2 square minus y square, because the height is the same in both triangles. So this is one relation, and x plus y you would know is 10 root 3, which we got from the original Pythagoras, and you can find the x and the y, and then you can use Pythagoras. But yes, good catch that it may not be equal. Cool. So again, just to recap, this is the big triangle. You figured this was 90 degree absolutely correctly. Then the Pythagoras gave us this, but this may not bisect. It would have if the two triangles were like, if the two radii were equal. But yeah, in this case it will be x and y, and because the height will be the same, so like just applying Pythagoras in those two sub triangles and equating the height, you get one relation in x and y, and x plus y is anyway equal to 10 root 3. You solve for x and y. The moment you get x, you or y, basically you just calculate this from the general Pythagoras theorem, twice it to get the common chord length. Cool. For the common area, once again, as we have mentioned, that it is easier to sort of break it into portions that we know. So this would be the common area, right? So let's just name it basically. So something. So it will be MNP plus MQN, right? Now the area of MNP, this area, how to find that out? This area is what? Nothing but a sector minus this triangle. This area of the segment MNP is nothing but the sector MNP, which is, or let's call it CMNP sector minus the area of triangle CMP, right? CMP we can anyways find out. Why? Because we just figured out x. We already know this is 10, this is 10. We just figured out x here, so we can calculate that readily, or we just actually figure out the common chord itself, right? So that the length of the chord, let's say, comes 20, so it will be a 10 10 20 or 10 10 15 or whatever triangle. 10 20 is not possible, but 10 10 15 or whatever triangle, and you can calculate the area of that. And for the sector, and that is where this additional part was added in the question. For the sector, what you need to do is the x, like the x, the 10, you can find out this angle, right? Or even if you know this and 10, you can find out this angle. You'll double that angle to get this entire angle, so you get the angle of the sector. So basically then pi r square into that angle by 360 minus the area of the triangle will give you this part of the shaded region. Similarly, you will do the same exercise for this circle basically, and then you will take the area of this sector, subtract the area of this triangle, and get this segment. If the radii were equal, then these two would have been equal area, so you could have just found one and multiplied it with 2. But since the radii are different, so obviously this circle, like since it is a bigger circle, it will form a bigger sector, right? So that is why you cannot just directly find one and multiply by 2, which you could have done for equal radii. So, but the process is similar, like in fact identical, that you will find the area of the sector, subtract the area of the triangle, get this area of the segment, and add them both. Any questions? And once again, segment area will always be calculated this way only, sector area minus triangle area. The angle of the sector you will need to find out by the trigonometry. Like for example, if this was let's say 5, x was 5 for example, so 5 over 10, this would have given cosine inverse of half, so which is 60 degrees. So this entire thing would have been 120, theta would have been 120. Okay, so this is also a pretty standard figure that you will see, that this and the last one that we discussed, that you will keep encountering in one way or the other. Or can we move on? ABC is a right triangle, right angle, let's see, such that AC 15. Yeah, this is a previous CAT question, popular one. Right angle C, ABC here, AC is 15, BC is 20. Yeah, CD is the altitude, so CD is the 90 degree here. Circles are drawn within triangles ACD and BCD. Something of this sort. P and Q are the centers, find PQ. Simple, if you can find both the radii, it will be just R1 plus R2. PQ is nothing but R1 plus R2, as you can see. Now, so the entire question becomes just figuring out what is R1, what is R2. It's a right triangle, there's a circle inside of it. It cannot be more obvious than that, you'll have to use properties of the in circle here for a right triangle, right? But there's a challenge. The challenge is that we know 15 and 20. We know that the in radius for a right triangle is nothing but perpendicular plus base minus hypotenuse by 2. So if we were seeing this triangle, do we know all of them? No, we don't know that, right? So similarly for this triangle, do we know everything that we need to know from for this formula to be applied? We don't know this, right? We only know that, okay, this is 15, 20, so this entire length will be 25. That is a Pythagoras inference, right? But we don't know the exact length of that. So how to find that out? So let's say this is x, this is y. Again, the same principle that we used in the last question, that the height is the common part between the two triangles. So basically what we can write is 225 minus x square is the same as 400 minus y square, because equating the heights again, like let's say if this was h, so this would be an equation for h from both of these small triangles. So this basically gives me that y square minus x square is equal to 175. Also, I know that y plus x is 25 from direct Pythagoras, like 15, 20, 25 is a Pythagoras triplet. Y plus x is 25, right? So basically, if you put that here, so y minus x would be 7, because y minus x into y plus x is 175, y plus x is 25, so y minus x is 7. So y minus x is 7, y plus x is 25. It is obviously clear that y is 16 and x is 9. You can solve it also, but yeah, y is 16 and x is 9. So essentially this is 16, this is 9. So in this triangle, now I know two sides. I actually know all the three sides because I can figure it out. This is 90, this is 15, there is 16. No, actually this would be 9 and 7. No, just a sec, it would be 9, 16 and 9 only, yeah. So this would be 16 then, yeah. And this would be 9. Right, so now I know that this is 15, this is 9. Just ahead and taking the x and the y. So then the 15 and the 9, the Pythagoras triplet, the height becomes 12. And you can check it in the other triangle also, it will come out the same. Right, 9 square and 12 square and 20. Or 16 square and 12 square, give you the 20 square. Right, so now I know all the sides, I can just directly plug it into this formula. So R for the above triangle would be what? This is the hypotenuse 15, the opposite as to right angle. So basically it will be 12 plus 9 minus 15 by 2, which is nothing but 3, which is R1. R2 would be from this triangle 16 plus 12 minus 20 by 2. So this is 4. Your answer PQ is nothing but 3 plus 4, which is 7. So it was very clearly evident from the question that right angle, there are circles inside of it, you need to use the in-radius formula in some way. The remaining question was to just figure out how to get to these numbers. Some of these were given, like for example 15 and 20 were given, 25 you needed to figure out. And how did we figure out the parts? That's directly equating the heights is always a reliable method. And then you got one equation, you know the sum. You solve for x and y, write them here, and then basically just calculate the height. You have all the sides. You find in radii, add them up for the intercenter distance, and you're done. So again, no fancy concept, and it's a previous CAT question. And actually subsequent CAT questions have gotten even easier than that. So yeah. Now there are three problems that you would see basically in standard textbooks, or like even they appear in mocks here and there, which is the 1 plus 1 ball problem, the 2 plus 1 ball problem, or the 3 plus 1 ball problem. Now what are they? We'll just derive the general results, and again, not to memorize it. So that is why the derivation is important, and it will also tell you a very useful method to deal with any diagram which looks similar to this. So 1 ball problem is nothing but that there is a ball that is kept here, and there is a smaller ball here. You are given this radius, you are asked to find the radius of the smaller ball. And there are many varieties of such questions where there are like 2 or 3 circles given. There will be a small circle inserted somewhere, and you need to find that radius. Always remember, all of these problems, the working of all of these problems revolve around formation of triangles. Again, as we had seen, in another theory part of this as well, that it is easier to sort of join the centers or join points that we know, and then form triangles out of them and work on those triangles. So always remember that area, like in such questions basically where your circles are getting inserted in like other spaces and stuff, so you need to form triangles, and then you need to continue the working from there. Now what triangles get formed depends on the problem. For example, here we'll see in the next problem, but it will always be a simpler triangle, like a right triangle, equilateral triangle, which are easier to work with. Right, as we saw, right, in that area question of where we had to find this area we again constructed a triangle only right there, and then subtracted the three sectors to get that middle area. Here also it will be similar, and it will be of use in every application with multiple circles. Cool. So let's say the capital R, or let's say the bigger radius is 1, just for an example, right? There is a center, this is a center, and you need to figure out what small r is. Okay, so now to figure this out, again, as just mentioned, you'll in 99% of the cases you need to make a triangle that is easy to work with. So here, and for that you have to join centers, because centers you would know, right? So this center is here, this center is here, just join the centers and just basically extend this to, like, make a horizontal and a vertical component of this line. So this line was this, just make a horizontal and a vertical component of this to make a right triangle here. This is small r, this radius is small r, this is 1. So I know that one side is 1 plus r. Now this entire radius would have been 1, but this part is again small r, this would have been small r. So how much will be this? This will be 1 minus r. Similarly, how much will be this? This entire piece, like from this to this point, it would have been 1. This to this is r, so it will again be 1 minus r. Let me just repeat. This is direct 1 plus r, just joining the center to center. This is 1 minus r because 1, and this is r, so 1 minus r is the remaining part of this triangle. Then this side of the triangle would be again 1 minus r because this is 1 and this is r. Right, now, okay, I have three sides of a right triangle. I can directly apply Pythagoras. So 1 plus r whole square, which is this side whole square, will be equal to 1 minus r whole square plus 1 minus r whole square. 2 into 1 minus r whole square. Now, here's the tiny catch of this, right? You can solve this Pythagoras theorem and it will 100% give you the correct answer for small r. No doubts, right? So, but it is a lengthier method to get to the correct answer. What I should directly observe is that the right triangle has 1 plus r, 1 minus r, 1 minus r. So it's an isosceles right triangle. And what is an isosceles right triangle? Basically, it is 1 is to 1 is to root 2. The small sides are 1, the bigger side is root 2. So what I can directly write is 1 plus r will be 1 minus r times root 2. Okay, again, no problem with this method at all. But the thing is that if you can make do without going into quadratic system, because what will happen is once you open the bracket, there will be a 2r square term here. And there will be r square here. So once you subtract them, there will still be an r square remaining, and you have to basically fight for quadratic. So why not save time and just use an isosceles right angle triangle 1 is to 1 is to root 2 ratio. So this would be 1 plus r is root 2 minus r root 2. So basically r would then be root 2 minus 1 over root 2 plus 1. You can rationalize this by multiplying root 2 minus 1 above and below. So this will be root 2 minus 1 whole square over root 2 square minus 1 square. So this will be 2 plus 1 and 3 minus 2 root 2, and denominator would be 1. So this is the small r value. If you calculate this value, it would be close to around 0.18. Close to that. To say that basically if there is a bigger circle kept this way, and the smaller circle is so that it just occupies the space left by the bigger circle. If the bigger circle has a radius of 1, the smaller circle would have a radius of 0.18 or 3 minus 2 root 2. Now if they just ask the similar problem that okay, if the bigger circle had a radius of 10, then what, or a radius of 6, then what? So we know that the small r was 0.18 in the case of the bigger circle being 1. So the smallest radius in this case would be 6 into 0.18, which is 1.08 over. If the bigger circle radius was 4, then what? 4 into 0.18, 0.72, you're done. And especially when options would be given, so you can easily see that what option sort of comes the closest to that. So this is the 1 plus 1 over, and pretty simple again, just creating this right triangle and just marking the sides in terms of the smaller radii and just basically putting it into this setup, right? Yeah, so this was 0.18. Now coming to the next one, which is a 2 plus 1 ball problem, and this was asked in CAT 2019 slot 2. So if somebody would have done this earlier, this would have taken 3 seconds or 4 seconds to do this in the exam. So 2 plus 1 ball problem is what? So 2 plus 1 is nothing but whenever you have these sort of, like, obviously the exam will not say a 1 plus 1 word problem. They'll either give you the figure and they'll mark you the dimensions, or they'll give you in terms of a word problem. For example, like they may say that, okay, like a ball is pushed against a wall, then in the space remaining between the wall and the ball, there is another smaller ball kept so that it just fits in. So if the radius of the bigger ball is this much, what is the radius of smaller ball? So this is just a different way to put it in English. But essentially what they mean is a one word problem. So again, converting the English to the maths is itself a skill. But once you've converted that, then and you've solved this before, like you just have, so it should be an instant problem. But yeah, converting that word to geometry, a figure, that's why like most of the problems here given will not have figures, so that we learn how to make those diagrams as well. But yeah, after getting to this point, then it's a direct cool. So in the 2 plus 1 ball setup, there are like two balls and there is a small ball kept here. Okay, so this is R and these are two identical balls. So again, let's say R equal to 1, R equal to 1. This is small r. So how to find small r? The problem statement is the same. Right, so let's just derive this for r equal to 1. In CAT, as you see that they ask the exact same question for r equal to 4, and then we'll use the same result. So basically, if you see the question that came in CAT, it was that touch externally, two circles touch externally, which are these two circles, and touch externally, as we just discussed, that means that they are tangential to each other, they touch at one point. Each of those is touched by a third circle, which is this one. If all the three have a common tangent, which is this one, find the radius of the third circle. So it's the exact same setup, no change. Okay, so this is the center, this is the center. Again, join the centers first. Of course, if I join this line to this, this will be 90. This is 1, this is small r, this is 1, this is small r, this is 1, this is 1. So this triangle becomes again an easier triangle to deal with because this triangle is isosceles with sides 2, 1 plus r and 1 plus r. Now I need to find small r, right? So this is an isosceles triangle. Fine. In the last one, we could have applied a 1:1:√2. Like that relation of 1:1:√2 held true because it was a right triangle directly. Here there is no direct right triangle. Like there are sub right triangles, but there's no direct right triangle. But you can make these sub right triangles as well here, right? So here, now if we see this perpendicular length, what is this going to be? We know that this entire thing is going to be 1, and this small part is going to be r because center to perpendicular to the tangent, this is going to be r. So this entire piece will be 1 minus r. So basically this height of this triangle essentially would be 1 minus r. So now if you see this right triangle, you know the sides. You can do this in two ways. We'll just cover both the ways. If you see the small right triangle, let's say give us something PQM. PQM that has sides 1 plus r, which is n, which is nq. So 1 plus r, 1 and 1 minus r. You can apply Pythagoras here. This square would be equal to this square plus this square. Yeah, so basically 2r and there will be minus 2r, so it will be 4r equal to 1, r equal to 1 by 4 or 0.25. You could have also done it the other way, that you could have calculated the area of the isosceles triangle using the concept that we had learned for isosceles triangle, which is b by 4, 4a square minus b square, and then you would have equated 2 base into height into half formula and find out the height. So that is also a way, but yeah, this is also works as well. So now it comes out to be 0.25, right? Which means that if all these two circles have like the radius of 1, then the small circle that just fits in between these two, it will be the radius would be 0.25, right? Now, if you've done this problem before in the exam, you know this. Now, two circles, each of radius 4 touch externally, each of those set by a third circle, each of those, all three have a common tangent. This one, find the radius of third circle. Now you know as soon as you make the diagram from this question that it's a setup that I've seen before. That's it. The problem is done. The radius here is 4. So the radius of the small circle will be 4 into 0.25, which is 1. Problem is done. So you can see the sort of the time benefit that you can have in an exam setup if even if you don't remember the result, but you know that something familiar or something like this you've seen before, it can save you quite a bit of time. Third and the last variety of this is a three ball problem, 3 plus 1. So which is nothing but as you would expect that there are these three circles and there is a circle, small circle in between this. This is a radius small r. Again, each of those three circles have a. So these are like a family of problems of these three problems: the 1 plus 1, 2 plus 1, and 3 plus 1. So that's why I like covered together. And this is like, even though this might look the more complex than the previous cases, this is actually the simplest. Why? Because here again, like this setup we have seen when we were calculating the area of this middle part, you need to join the centers and it will be an equilateral triangle, which is the easiest triangle to work with. So 1, 1 is all 1 actually. So 1, 1, 1, 1, 1. So it's an equilateral triangle of side 2. Done. Okay. Now, equilateral triangle has like offers us a wide variety of liberties actually, because of the simple fact that everything in equilateral triangle falls at the same point, right? So like, so basically the height will be the altitude will be the angle bisector, all of them will be the like the median, and so on and so forth. So everything is the same, right? Okay. So now if you have this particular, if you again, similar to what we've done for the initial problems right there, if you basically draw this line, right? Now this would be 1 because radius, and this would be r. So this particular line PQ, let's say this center is P for the small circle and it's Q here. So PQ would be 1 plus r, which we know. Okay. Now this is an equilateral triangle, right? So what we can do is we can find out the height here. Like basically if we continue this till the end, we can find out the height there, right? And 2/3 of that height will be this length. Why 2/3? Because this point will be the all, like every point, this will be the centroid, this will be in center, this will be the circumcenter, this will be orthocenter, everything, because equilateral triangle everything is the same. So this is where that point comes. So this length will be nothing but 2/3 of the height because of the 2:1 median ratio. Or if this is confusing you, you can also do it this way, that this angle is 60, so this angle will be 30. You can use tan 30 in one of the triangles to figure that out, right? So basically the whole question then becomes just figuring out the height of this equilateral triangle, and you're done. 2/3 of that will give you this length, you put that to 1 plus r and over. So height of an equilateral triangle is what root 3 by 2a. So here it will be root 3 by 2 into 2, which is root 3. 2 by 3 into this will give me 2 by root 3. This is equal to 1 plus r due to 2:1. So 2 by root 3 minus 1, which is equal to 2 minus root 3 by root 3. And this, if you sort of try to convert it into a approximate decimal, right? So this will be approximately equal to 0.16, which is the result for the 3 plus 1 wall problem. But it's again very important to know the method as well, so that even if you don't recall these, you can quickly derive these, and all these are very short derivations, right? Like even for the 3 plus 1, which seemingly looks complex, so it seemingly looks a bit trickier, but it's a yeah. So the approach is not as tricky at all as the question would have looked. And just the fact that equilateral triangle, we can use those liberties. And we should use those liberties wherever possible. So even in like other areas of geometry, right? Whenever you see equilateral triangle, just remember that you can apply everything there. The 2:1 ratio you can apply there. The angle bisector properties you can apply there. Circumcenter, orthocenter properties you can apply everything there. Like here we applied the 2:1 piece. Okay, so just to summarize, the 1 plus 1 gave us approximately 0.18. 2 plus 1 gave us 0.25. 3 plus 1 gave us 0.16, for if the bigger circles had a radius of 1. So if they change it to another multiple, you just need to multiply this with that number and get the answer. Okay, would suggest you to, like, even if you cannot keep this in mind, the method should definitely be clear so that it takes lesser time in an exam setup. And time is either your best friend or your worst enemy in there.